I'm working at the interface of the particle physics and cosmology, which has aim to explain the past history of our universe and the present status of our universe. Also, it is to predict, if it is possible, the future of our universe. There are several important topics in the cosmology, especially modern cosmology. It is based on the so-called inflation physics. The inflation is a phase in which the expansion of the universe is being accelerated. It is supposed to occur in the very early history of the universe. So it resolves many the non-trivial puzzles in the old Big Bang cosmology. However, it is quite non-trivial to realize the inflation idea in the well-motivated theoretical framework. So one of the research I'm focusing on is a constructing of the inflation model, which can realize the inflation in a manner consistent with the various the observations. Another important topic that I'm focusing on is so-called dark matter physics. The dark matter is turned out to occupy most of the energy density of matter energy density of our universe. So, roughly speaking, 85% of the matter contents in our universe is occupied by dark matter. The name dark matter means it is invisible, basically. So the existence of this dark matter is obtained. The evidence of dark matter is only from the gravitational effect. So we don't know the other property of dark matter. For example, its mass and its coupling to the visible matters and how it is produced in the very early universe. So the study I doing is a construction of dark matter models and the investigation of the possibility of detecting the proposed dark matters in certain theoretical framework. Those things are the researches what I'm doing nowadays, and recently I'm doing some research on the so-called the lepton number asymmetry of our universe. It is related to the neutrino physics, but it has some important impact on the present status of the universe. So nowadays I am doing or constructing or trying to understand how this the lepton number asymmetry of a neutrino can be consistent in a given theoretical framework, and also how I can make some plausible prediction for this the lepton number asymmetry which might exist in our present universe. If I introduce my recent work about this the lepton number asymmetry in our universe, and the motivation of the work was the discrepancy of current expansion rate coming from, for example, various different observations, for example, CMB and the supernova data. So there is a discrepancy between these two. The estimation, the discrepancy is around 3 point something sigma. So there are several possibilities of explaining this discrepancy. One of the possibility is the adding so-called the dark radiation, defined as so-called delta N effective, and it can be from this the lepton number asymmetry of neutrino. So when the lepton number asymmetry of neutrino is quite large, you can obtain this large delta N effective, and this existence of a sizable delta N effective can explain the discrepancy of these estimations of H naught in various different observations. So we are trying to see the details of this physics related to this electron-based symmetry in regard of delta n effective. That's one the project we are doing nowadays. And if I go a little bit more about this the things, then there is some the important feature in this research. One of them is we have to distinguish the mass eigenstate and the flavor eigenstate when we calculate this electron-based symmetry of neutrino. So that is the quite important aspect when we estimate this delta n effective. So it has been done recently, and it has the crucial importance in the analyzing the property of our current universe. Thank you.